Here's our last homework video on linear approximations. So we know if we zoom in on a function, no matter what the function looks like, whether it's concave up increasing, concave up decreasing, concave down increasing, oops, concave up decreasing looks like that. Concave down increasing, concave down decreasing. If you zoom in, these functions will look like linear functions at a specific point. So take, a point here. If I zoom in here, 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 it's going to be looking like a linear function. So that means when we use tangent lines, I'm going to have to go this way. On our function, our tangent line is going to do a very good job of approximating what is actually happening on the function. So if I draw a tangent line here, tangent line there, tangent line here, tangent line here. Those tangent lines at this location where we zoomed in at will do a very good job approximating what the function looks like. So if I want to approximate points, like that point on the function, this point on the function, this point on the function, this point on my function, and I'm using the tangent line, first of all, I notice the tangent line is very close to the location of that point. And we can see that these points on my tangent line would be what we would get as an approximation for the function value. And we can see when the red dot is over the black dot, like in this situation, that our approximation is over the actual. If it's underneath it, it's an under approximation. So this would be an under approximation. This would be an under approximation. This would be an over approximation. This would be an over approximation. So looking at this, notice I put some points on the right, I put a couple points on the left, or I guess I put 1 point on the left. It doesn't matter if your function is increasing or decreasing when determining over or under. It's actually no. Doesn't matter which side of the tangent line point. No. Concavity will determine over or under approximations, regardless of the side. Okay? All right, so here I've given you a table of values of function f. Find the best approximation for the function value that you're looking for here, 2.8, 2.1, 4.25. Well, first off, we know that approximations are going to be more accurate the closer we are with our tangent line point. Like if I wanted to try to approximate maybe a point all the way up here, I might not use this point here. I might use a closer point where my tangent line would be better approximation of that point there. So it's very important is to pick a point that's close to the value you're trying to approximate. Here, 2.8, that is close to 3. So I'm going to use f of 3, which is 2, and f prime of 3, which is 5. And I'm going to create a tangent line equation. Y minus 2 equals 5 times x minus 3. And I'm going to approximate f of 2.8 by plugging 2.8 in for x. So I get f of 2.8, and that's what I replaced like y with, and then I added 2 to the right side. F of 2.8 is approximately 5 times negative 0.2 plus 2. 5 times negative 0.2 is negative 1. We need to be able to do these calculations by hand. You can do it by hand like this. You got 5 times 2 is 10. You got a decimal place. We got the negative. Boom. So negative 1.0 plus 2, that's going to be 1. F of 2.8 is approximately 1. All right, so f of 2.1, I'm not going to use this equation, 3, 2, because I have another point that's closer to 2.1. X equals 2. So I'll use f of 2, which equals 4, and f prime of 2, which is negative half. Okay, so I got y minus 4 equals negative 1/2 x minus 2. And I'm approximating f of 2.1. So f of 2.1 is what I'm trying to approximate. Add 4 to both sides. Negative 1/2, plug in 2.1 for x. And this would be my approximation. I have f of 2.1 is approximately negative 1/2. I'm probably going to change that to negative 0.5 times 0.1 plus 4. It's important with like 1/10, 10, you move the decimal place over. So 0.5 times 0.1 would be 0.05. Plus 4, so f of 2.1 is going to be approximately 3.95. Another way to do 0.5 times 0.1 is this. Move the decimal place. Since you have 2 decimals to the right of the decimals, you move the decimal place over twice. 1, 2. Okay? Or 0.1, move it to the left 1. F of 4.25, I should be using this point at 4 would be my closest to 4.25. So my tangent line equation would be close to where 4.25 would be. I got the point 43 and a slope of 2. So my equation y minus y1 equals m times x minus x1. Approximate f of 4.25 if we don't know. So instead of y, f of 4.25, add the 3 over. It's approximately 2 times 4.25 minus 4 plus 3. So 4.25 is approximately 2 times 0.25 plus 3. In this case, it's probably easiest to change this into a fourth. Not necessarily in this case, but we see it's 1/2 plus 3, so 3.5. 6/2, 7/2, or 3.5. All right. All right. If f double prime is positive, are your approximations over or under? Okay, great. This is a random question. If my second derivative is positive, that means I'm concave up. My approximations, no matter where I draw my tangent line, would be under. Cool. Approximate the following square root values using f of x equals root x and the points on the function that you know. Root 5, root 3.9, root 9.25, root 10. Okay, well, first things first is we should be understanding that there are points, f of 4, root 4, which is 2, that I should be using. When x is 4, that's close to 5, root 5, 3.9. And here, f of 9, I know what the square root of 9 is, 3. So depending on my situation, I'm going to use these different points. And then I'm also going to be using the slope at these two different points. Remember the tangent slope generator for root x is 1/2 x to the negative 1/2, or 1 over 2 root x. So f prime at 4 would be 1/4. Plugging in 4 into this is 2. F prime of 9 would be 1/6. All right, so the equation, my tangent line that I'll use to approximate both of these values is y minus 2 equals 1/4 x minus 4. Now, this is what's really tricky. People are like, do I plug in root 5? It's like, no, you don't plug in root 5. You don't do that. We want to approximate f of 5, which gives us root 5. F of 5 means x equals 5. Here we want to approximate f of 3.9, which gives us root 3.9. So we need to use the x equals 3.9. So that's important. If I want to approximate root 5, I'm going to be thinking about approximating f of 5. Again, f of 5 will replace y. 5 will replace x. Add the 2 over. I get 2 plus 1/4, so 2.25 or 9/4. Let's approximate f of 3.9. That'll be 1/4. Use x equals 3.9 minus 4 plus 2. 1/4 times negative 0.1 plus 2. This is where I'm going to probably switch to 0.25 times negative 0.1, because when I have a 0.1, I know I'm just going to move the decimal place over once. So this ends up being 0.025, that's negative, that I'm adding to 2. I think f of 3.9, which is this root of 3.9, is approximately 2 minus 0.025, what's that going to be? I mean, let's just do the math. 200, 0.025, so 19, that turns into a 9, that turns into a 10, so that's 5, 7, 1.975. Yeah, 1.975. Okay, let's do the same thing over here. Now, I'm using a point that I do know that is close to the x values 9.25 and 10. So my equation of my tangent line that I'm going to use, y minus 3 equals 1/6 x minus 9, that I'll use to approximate f of 2.9, so that's x equals 9.25, and f of 10, which is x equals 10. So let's do it. F of 9.25 will be approximately, plug that in for y, add 3, plug 9.25 in for x, not root 9.25, 1/6, 9.25 minus 9 plus 3, which is 1/6. I'm going to change this into 1/4. It'll be easier for me to do.
Good morning, teachers and staff. Just a reminder, we do have a fabulous breakfast over in the annex workroom. Teachers and staff, don't just start here to be hungry. Run over to the annex and get some food. and make it a great day.
So I end up with 1/6 times 1/4, which is 1/24, and I need to add that to 3. So that's 1/24 plus 72/24. I just did the math on that, which will be 73/24. So I think the square root of 925 is approximately 73/24. And f of 10, so root 10 is approximately 1/6 10 minus 9 plus 3. That's 1/6 plus 3. 18/6, so this is 19/6. So I think the square root of 9.25 is approximately 73/24. I think the square root of 10 is approximately 19/6. Out of the two sets of 2, which one will be more accurate compared to the original? Why? So the ones that are closer to the point that I'm using on the function, I have a point 4, 2 on the function root x. 3.9, the x value of 3.9 is closer to 4 than the x value of 5. So my approximation for 3.9, which is approximately 1.975, and my approximation for 9.25, which I said is approximately 73/24, that will be closer than the others because the x values or the location on my function is closer to the tangent line point that I know. And then the others. I'm going to go ahead and confirm that. So root 3.9, the actual value is 1.9748. I thought it was 1.975. Very, very close to 1.974. Very, very good approximation. Meanwhile, the square root of 5, I said was 2.25. It's actually 2.236. So I'm off in terms of a hundredths decimal place, whereas my approximation for root 3.9 was out to the thousandth. Okay, let's do the same thing for root 9.25. It's actually 3.04138. I think that's going to be close to 73/24. That is awesome. I'm accurate to the thousandths decimal place. And then let's look at root 10, which I think is close to 19/6. It is, but it's just a little less accurate. Examine the concavity for root x. Is f of x concave up or down for x is greater than 0? Are my approximations over or under? So I already have the first derivative. Let's take the second derivative. The first derivative is 1/2 x to the negative 1/2. The second derivative will be negative 1/4 x to the negative 3/2. So that's negative 1 over 4x to the 3/2. If I'm talking about plugging in values greater than 0, because I'm not plugging in any values that are less than 0, into this, I'd have a -1 divided by a positive times a positive. So that means this is a negative. So f double prime is negative. That's telling me f is concave down. So my function is concave down. Since my function is concave down, I know my approximations are over the actual. And since they are over, that is confirmed when I use my calculator. You're not going to be using your calculator to do this, but you see your approximation 1.66, 1.62, 3.0416, 3.0413. So all my approximations over the actual. All right. All right, new one. I want to approximate f of 1.1 given this function. So like, here's the whole key to approximations. We don't know how to do this stuff by hand, like 1.1 cubed plus 1.1 squared plus 1.1. Don't try to do this, okay? I've seen people on quizzes like actually try to do this because they don't know what they're doing. This is not the key to the lesson. The key to the lesson is we are using a tangent line at a point that we do know that is easy to work with to approximate tough function values. So what would be the point that's close to 1.1? 1. F of 1 I know is 3. 1 plus 1 plus 1 is 3. That's great. Well, what is the tangent slope at that location? Well, before I find f prime at 1, I need to find f prime at x, the tangent slope generator, 3x squared plus 2x plus 1. This tangent slope generator at 1, 3 plus 2 plus 1 is 5, 6. So f of 1 is 3, f prime of 1 is 6. I have my equation of my tangent line at 1, 3. This, I say, and I'm just going to write this down just for emphasis, this mimics f of x, which is x cubed plus x squared plus x, around x equals 1. So since that mimics f of x around x equals 1, it'll do a good job of approximating f of 1.1. F of 1.1 is the y. Add the 3 over, plug in 1.1 for x. I think it's 6 times 1.1 minus 1 plus 3. That's 6 times 0.1 plus 3. That's 0.6 plus 3. That's 3.6. So I think f of 1.1 is approximately 3.6. Watch. 1.1 cubed plus 1.1 squared plus 1.1 is approximately 3.6. Boom. That's the key to tangent line approximate. All right. Approximate the cubed root of 9. Use the correct function tangent line at the correct point. This is great. You need to be able to understand like the function to use and the point on the function to use. I should be using the cubed root of x, that function. And there's one point that I know the cubed root of that is close to 9. 8. The cubed root of 8 is 2. 2, 4, 8. So 8, 2. I need the tangent slope generator at that point. I have the tangent slope at that point. I have 1/3 x to the negative 2/3 as the tangent slope generator, 1 over 3 x to the 2/3. I need f prime of 8. That's 1 over 3 times 8 to the 2/3. Please know how to do 8 to the 2/3. That's 8 to the 1/3 squared. You can write it, this fraction, as a power to a power. That's 2 squared, which is 4. 4 times 3 is 1/12. So I got 8, 2, and the slope of 1/12. The slope is 1/12. So y minus 2 equals 1/12 x minus 8. This mimics the cubed root of x around x equals 8. Okay, so I want to approximate the cubed root of 9, but that's like approximating f of 9, the cubed root of 9. So make sure you understand you're approximating f of 9. I'm not plugging in the cubed root of 9 here. I don't know what it is. I am instead plugging in 9 for x, adding 2 to get the approximation of the cubed root of 9. I get 1/12 plus 2. 2 plus the 12th, that's 24 twelfths. I get 25 twelfths. So f of 9, which is the cubed root of 9, I say, is approximately 25 twelfths. Okay, watch this. 9 to the 1/3. Order of operations. .0800, 25 twelfths. 2.083. All right, given the graph of a function, draw a secant line s of x from 1 to 3, a tangent line t of x at 2. Order the following values from least to greatest: f of 2.1, s of 2.1, and t of 2.1. Okay, so this is f of x, okay. And there's two things that they want. They want a secant line from 1 to 3. We have some concave down increasing function. Here is my secant line. Okay, so that's s of x. I got a tangent line at 2. Okay, here's my tangent line at 2. It looks like we got a mean value theorem situation where maybe the tangent line is equal to the secant line. Sure. This is t of x. And I got my function f of x. Order from least to greatest f of 2.1. Well, f of 2.1 is right here. T of 2.1 is right here. It's an over approximation. So it's above the f function. And then s of 2.1 is down here. They should be lined up on top of each other because we're talking about just one x value. So notice from least to greatest, I have s of 2.1, which is less than my f of 2.1, which is less than my t of 2.1. Okay, so just looking at approximations over and under using different lines. Let's look at the same thing here from 1 to 3, talking about a decreasing concave up function. Here's my secant line, s of x. Here's f of x. My tangent line at 2. Again, similar to like a mean value theorem situation. And let's look at 2.1. I got s of 2.1 in blue. When x is 2.1, s would be like right there. I got f of 2.1 right there. And I got t of 2.1, which is right here. So from least to greatest, now my tangent approximation is under my actual function value. And if I used a secant line to do approximations, it would be over. Okay. Would your answers change if f was negative? So if this was all below an x-axis, no. I mean, this would still be the most negative, so it'd be the least value, then in the middle, then the most positive. And then this would be the most negative, this would be in the middle, this would be the least negative. So in terms of least to greatest, no. All right, pi over 2 is approximately 1.57. Approximate 1.5 for f of x equals 3 cos x minus 1 using the tangent line to f of x at x equals 2. Okay. So first of all, let's find the point, f of pi over 2, which is -1. Great. Let's find the tangent slope. F prime of x equals, remember 3 cosine x, 3 times a function, a constant times a function. Its derivative, you do not need to use the chain rule. It is just a constant times the derivative of the function. So I have 3 times negative sine x. I wrote it as -3 sine x. And I need to find that at pi over 2. Sine of pi over 2 is 1, so this is -3. Okay, so my tangent line, which will do a good job of approximating this function at pi over 2, is y plus 1 equals -3 times x minus pi over 2. Trying to approximate what f of 1.5 is. This is not a great question because I got this problem right here. Like, what is that? I mean, I could say it's 1.57, so this is 0.07. And maybe I do that, but instead, like, I don't know. It's not great because I'm using pi. Let's do that. 1.57. That's 0.07 negative. So I got -3 times -0.07 minus 1. So that'll be positive 0.21 minus 1, which is 0.79 negative. Yeah. Is that going to be good? I don't think it's going to be great. I think it'll be decent. Watch. 3 times cosine, make sure you're in radian mode, 1.5 x minus 1 is approximately 0.79 negative. I mean, pretty good. But the problem is, like, I'm using an approximation for an approximation rather than using an actual value for something like that. So we're good. It still worked out. All right, given f of 1 equals 5, f prime of 1 is 2, f double prime is positive. Could the following values exist on f of x? F of 2 equals 7. Question mark? Yes, no? Good question. This is a good question. So if I have this information, I know I got the 0.15. Here's what I know. I'm going to do this visually. If I have the 0.15, the slope is 2 at that location. But my function is concave up. Okay? If I use the tangent line, y minus 5 equals 2 times x minus 1 for 2. Two plus 5, which is 7. Okay? My approximation is 2, 7. Could that be the actual value on f of x? The answer is no, because f of 2 equals 7, I know, is under, which means 7 can't be the actual. Let me do a better job of drawing this picture. One 5, slope 2. Tangent lines are tough. That stinks. Okay. 1 5, slope of 2. My approximation is 2 7. But I know it's under because my function is concave up. So can't be 7. Could it be 8? Yeah. Because 2 7 was under. Could it be 6? Nope. Because 2 7 was under. See what I'm talking about? So could the value, actual value exist? That's what we're going with. Let's look. Same deal. We got -2, -3. I got a slope of 4. I got a second derivative that's negative. So equation of my tangent line, y plus 3 equals 4 times x plus 2. I'm looking at f of -3. Well, f of -3 will be approximately 4 times -3 plus 2 minus 3. So that's -4 minus 3, which is -7. So let's think about this visually. I got a point -2, -3. A second derivative that's negative, which means I'm concave down. Maybe it's concave down, decreasing, increasing, it doesn't matter. And a tangent line. My tangent line is going to be over. So I'm looking at -3. This is -2. I'm looking at -3. I know that's still going to be over. Gosh, it's so hard to draw. I'm going to get rid of the x and y axis. Boom, boom. Horrible. Boom. Not great. Ugh. Ugh. Whatever. It's not good enough. Should have paused. There we go. All right. So my approximation, which is -3, -7, is over. So since my second derivative is negative, could -3, -7 be the actual? The answer is no. Because f of -3, which equals -7, is an over approximation. Could I have f of -3 equals -6? No. Again, because f of -3, -7 was over. It's got to be under, and by under it needs to be more negative. So f of 3 equals -x? Yes. We could have the value f of 3 equals -8. All right, last one. F of x has 1, 0. Use the tangent line at x equals 1 to approximate the location of the 0. 0 is when we have an x coordinate that produces a y of 0. I got f of x, I got the log function. Its tangent slope generator, 1 over x plus 3x squared. If we want to find the tangent slope at 1, I get 1 plus 3, which is 4. And if I want to find the point at 1, f of 1 would just be equal to 1. Log of 1 plus 1 cubed. That's just 1. Okay, so I got y minus 1 equals 4 times x minus 1. I'm trying to approximate the location of a 0. So I'm trying to find x when y is 0. I'll maybe write that down. So I got 0 minus 1 equals 4x minus 4. Add 1. Probably add 4, actually. I get 3 equals 4x. X equals 4/3, 3/4. Add 4. It's 3, 3/4. Okay. So let's look. Log x plus x cubed. Got 1, 0 right here. I can find where it intersects with y equals 0. I think it's close to 0.75. 0.70. Okay, so there you go. That's linear approximations. This is a good homework. I like what I did with this homework. So hopefully we understand what's going on. Thank you.